Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The formal presentation in 1798 of the paper, titled Experiments to Determine the Density of the Earth, by Henry Cavendish, marks a culminating moment in the history of experimental physics. This document, published in the Philosophical Transactions of the Royal Society of London, represents a profound achievement in quantitative measurement, a feat of such precision and conceptual elegance that its results remain astonishingly accurate over 2 centuries later. The work's purpose was direct to ascertain the mean density of the terrestrial globe by measuring the gravitational attraction between known masses in a laboratory setting. This essay will undertake a rigorous, section-by-section evaluation of the internal claims, arguments, and specific methodologies presented within Cavendish's foundational paper. The analysis will proceed sequentially through the work's logical divisions, assessing the coherence of its reasoning, the ingenuity of its apparatus, and the soundness of its conclusions, all based on the evidence and framework Cavendish himself provided. It is an exploration into the anatomy of a masterpiece of scientific inquiry, revealing the meticulous craftsmanship underlying one of physics' most celebrated measurements. Section 1, the conceptual framework and intellectual acknowledgement. Cavendish commences his paper with a lucid and concise declaration of its ambition. He frames the central problem as a comparison. A force of gravity exerted by the entire Earth upon an object is a familiar phenomenon, expressed as its weight. The challenge lies in making the gravitational attraction of a much smaller, known mass tangible and measurable. By quantifying this minuscule force, a direct ratio could be established between the mass of the laboratory object and the mass of the Earth, thereby yielding the planet's density. This initial claim is one of elegant simplicity, reducing a cosmological question to a terrestrial, mechanical problem. He immediately follows this by establishing the intellectual provenance of the experimental design. He generously and explicitly credits the concept and the initial construction of the apparatus to his friend, the late Reverend John Mitchell. Cavendish presents himself as the inheritor and executor of Mitchell's vision, a claim of stewardship that shapes the entire narrative. This framing is a critical element of the paper's character. It positions the work as the completion of a shared scientific goal, with Cavendish's contribution being the fastidious attention to detail, the refinement of the apparatus, and the relentless execution required to bring a brilliant idea to a successful empirical conclusion. The initial claim, therefore, fulfilled one of a clear scientific objective and one of honest intellectual lineage, setting a tone of collaborative spirit and scholarly integrity from the hour. Section 2, the architecture of precision and isolation. The second major portion of the paper is dedicated to an exhaustive description of the experimental apparatus, a construction now known as the torsion balance. The claims made in this section are implicit in the design itself, each component representing a solution to a specific physical challenge. The core of the device was a light, 6-long arm of fir deal, suspended at its centre by a slender wire of silvered copper. At each end of this arm hung a small lead sphere, 2 inches in diameter. The central claim here is that this suspended system is exceptionally sensitive to many horizontal forces. The torsion, or twist, in the suspension wire would provide a restoring force proportional to the angle of rotation, allowing any deflecting force to be measured. The genius of the design, and the focus of Cavendish's detailed exposition, lies in the methods used to isolate this delicate system from all conceivable disturbances. He describes constructing a dedicated room, or closet, to house the balance, with its walls being 2 feet thick to provide thermal stability. Furthermore, he operated the entire experiment remotely from an adjoining chamber. This claim of remote operation is crucial. By using a system of pulleys and ropes, he could rotate the large attracting masses, 2 massive lead spheres each weighing nearly 350 pounds, into position without ever entering the instruments chamber. This design element constitutes a powerful argument for the elimination of the experimenter's own body heat and gravitational influence as sources of error. Every detail of the construction, from the choice a light for arm to minimize its own inertia to the gilt paper on the arm to reduce radiative heat effects, supports the overarching claim that the apparatus was engineered for supreme stability and sensitivity, capable of registering a force less than 1/50,000,000th of the weight of the smalls. Section 3. The observational methodology and measurement protocol. Having detailed the static architecture of the experiment, Cavendish next elaborates on its dynamic operation, the protocol through which he extracted his data. This section makes a series of claims about the validity and reliability of his measurement techniques. His primary task was to measure two key quantities: the tiny angle of deflection of the balance arm when the large masses were brought near, and the natural period of oscillation of the arm when left undisturbed. For the deflection, he invented a brilliant optical system. He affixed a small slip of ivory, engraved with a vernier scale, to each end of the arm. He then observed this scale through a telescope mounted on the wall of the outer chamber, illuminating the scale with a small lamp. The claim here is one of high precision. This optical lever system magnified the tiny physical movement, allowing him to read the arm's position to 1/100th of an inch. To determine the arm's equilibrium point, or point of rest, he employed a method of averaging the turning points of the slowly decaying oscillations, a standard technique for finding a true mean position in the presence of damping. For the second crucial measurement, the time period, he would set the arm oscillating and meticulously time its motion with a clock, counting the vibrations over an extended interval. The claimed significance of this measurement is profound. The period of oscillation is determined by the moment of inertia of the arm and the torsional stiffness of the suspension wire. By measuring the period, Cavendish was effectively calibrating the very force he was trying to overcome. A longer period implied a weaker, more sensitive restoring force from the wire. Thus, his observational protocol established a self-calibrating system where one dynamic measurement, the period, provided the necessary constant to interpret the other static measurement, the deflection, in absolute terms. Section 4. The mathematical, were coarse to a terrestrial density. The subsequent section of the paper presents the mathematical framework that connects the empirical measurements to the final desired quantity, the Earth's density. The argument is presented with clarity and logical rigor, forming an unbroken chain of reasoning. The central claim is that the laws of mechanics and gravitation, as understood through Newton, can be applied to his desktop apparatus to yield a cosmological result. He begins by formalizing the physics of the torsion balance. He states that the torque, or twisting force, exerted by the suspension wire is proportional to the angle of deflection. He then connects this to the period of oscillation using the formula relating the period of a harmonic oscillator to its moment of inertia and the restoring force constant. In full spoken form, the square of the time period of one oscillation is directly proportional to the moment of inertia of the arm and inversely proportional to the elastic force of the wire at a given deflection. This allows him to calculate the exact magnitude of the wire's restoring torque from his timed measurements. Next illuminates the force exerted by large lead spheres on small. This is a direct application of Newton's law of universal gravitation, where the force equals a constant of proportionality, multiplied by the product of the masses and divided by the square of the distance between their centres. He carefully accounts for the geometry, considering the force from both large masses on both small masses. The core of his mathematical argument is the simple, elegant claim that at the point of maximum deflection, the gravitational torque exerted by the large masses is perfectly balanced by the restoring torque of the wire. By equating these two expressions, he can solve for the one remaining unknown, the constant of proportionality. In Newton's law, what we today call the gravitational constant, however, Cavendish frames his final step differently. He compares the calculated force of the lead sphere on the small ball with the force of the Earth on the same small ball, which is simply its weight. This comparison yields a direct ratio of the mass of the lead sphere to the mass of the Earth, adjusted for the relevant distances. Since the volumes of the sphere and the Earth are known, this ratio of masses directly translates into a ratio of average densities. The logical progression is watertight, a beautiful demonstration of how carefully collected mechanical data can be transformed through mathematical reasoning into a profound statement about the planet's fundamental composition. Section 5, an evaluation of the empirical record. Cavendish follows his theoretical exposition with a table presenting the complete results of his 29 individual experiments. This section makes the implicit claim that the data, taken as a whole, are consistent and converge upon a reliable mean value. The table is a model of scientific transparency. For each of the 17 distinct experiments presented, he records the date, the ambient temperature, the time of day, the measured point of rest, with the weights in both positive and negative positions, and the observed time of oscillation. From these raw figures, he computes a value for the Earth's density. The presentation of this complete dataset allows the reader to follow his work and assess the variability of the measurements for themselves. An evaluation of this record reveals a remarkable consistency, while the individual results show a predictable spread, ranging from a low of 4.88 to a high of 5.79 times the density of water. They cluster tightly around a central value. Cavendish's approach is statistically sound. He takes the mean of his results as the most probable value. He makes one notable exclusion, stating that the result from the very first experiment is omitted from his final average, arguing that he was still accustomed to the motion of the arm. This claim of improving experimental familiarity is a common and legitimate practice in fine measurement, reflecting an honest assessment of his own learning curve. His final average, derived from 23 valid observations after accounting for a few other minor adjustments he details, is 5.48 times the density of water. The table of results thus serves as the empirical bedrock of his paper, a public record that substantiates his claims of precision and provides compelling evidence for the robustness of his final conclusion. Section 6, a rigorous accounting of error and correction. Perhaps the most telling testament to Cavendish's genius as an experimentalist lies in the final sections of the paper, where he meticulously considers and attempts to quantify potential sources of systematic error. This portion of the work makes a powerful claim about the thoroughness of his scientific practice. He demonstrates an acute awareness that a measurement is only as good as its uncertainty. He devotes considerable space to analyzing the influence of temperature. He hypothesizes that if one of the large masses were warmer than the air inside the case, it could induce convection currents that would push the small ball away, mimicking a weaker gravitational force. Conversely, a colder mass might pull the ball closer. He performs calculations to estimate the magnitude of this effect and concludes that a temperature difference of even 1 degree Fahrenheit would be significant. This led him to wait for many hours after moving the weights to allow for thermal equilibrium, a decision directly supported by this analysis. He also addresses more subtle gravitational effects. He calculates the gravitational attraction of the large mahogany case itself on the balance arm, a claim of being so thorough as to account for the apparatus' own self-interference. He computes this force and finds it to be negligible, but the act of computing it is what signals his high standard of rigor. He further refines his main calculation by accounting for the fact that the large masses attract the fur arm of the balance, as well, a second-order correction that a less careful physicist might have ignored. Evaluating this section reveals a mind obsessed with precision, while later analyses, particularly by always a century later, would show that thermal gradients had a more complex and larger effect than Cavendish estimated. His explicit engagement with these problems is what elevates the paper. He claims to have considered and mitigated the major sources of error, and his detailed reasoning provides strong support for that claim, establishing a new benchmark for what constituted a complete and convincing physical experiment. Conclusion. In summary, a systematic evaluation of the claims within Henry Cavendish's 1798 paper reveals a work of extraordinary intellectual and practical integrity. From its honest acknowledgment of Mitchell's contribution to its exhaustive description of the apparatus, the publication, lays a transparent foundation for its conclusions. The claims of precision in the observational method, particularly the novel use of a remote optical lever, are convincingly demonstrated. The mathematical framework linking the laboratory measurements to the Earth's density is presented with impeccable logical coherence, a direct and sound application of Newtonian principles. The full publication of his raw data speaks to a confidence in the results and a commitment to empirical evidence. Most impressively, his detailed analysis of potential errors and corrections showcases a modern scientific sensibility, a deep understanding that controlling the experimental environment is paramount. The ultimate result, a value for the Earth's mean density of 5.448 times that of water, is a figure that stands remarkably close to the currently accepted value of approximately 5.515. This small discrepancy does little to diminish the achievement. On the contrary, it highlights the profound success of his methods. Cavendish's laconic and understated prose conceals the immense difficulty of the task and the brilliance of its execution. He believed he was weighing the world, and by meticulously documenting his every step, he provided a powerful and enduring argument that he had, for all practical purposes, succeeded. The paper remains a masterclass in the art of experiment, a testament to the power of solitary, focused inquiry to resolve questions of a cosmic scale.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.